This year, the SAS team worked with LAS to research and prototype a process to quickly fine-tune and deploy object detection methods on new video data without requiring mass labeling. This video will go over the 4 modeling methods and refinement methods used to generate object-specific label suggestions. This process flow summarizes each of the steps we have proved out throughout our year's work. Yellow boxes are where AI and ML methods can be implemented, and the white circles are where the human steps take place, first in identifying the object and data of interest, next labeling the model-generated suggestions, and finally assessing the model performance in an operational setting. The team received 863 video files, which we parsed into image frames for our computer vision model processing, resulting in just over 52,000 images. These images were collected between April and May of 2022 and comprised of 3 camera vantage points, seen here, that originate from within a moving car. We were asked to identify all CCTV cameras present, which are both rare and small objects within the collection frames. Rare and small objects traditionally are not well detected with generalized models that tend to do better on more common and larger objects such as cars or people that you can see listed here. Based on the 52,000 images, we assessed 4 methods for our initial approach. Segment anything with clip being the first one. We took Meta AI's Segment Anything model, and that parses the images into masks, segmenting out every single object within the frame. From there, the team ran clip embedding similarity to the phrase CCTV and prioritized the results by highest CCTV score, comparing to other common categories such as people, cars, billboards, and saw how many the clip score for the CCTV similarity was higher than all the other common objects. This resulted in 1.2 million suggested CCTV objects. Now you can see the distribution of the clip CCTV score, and we can click through each of these scores and see the exact mask bounding box and the image frame itself. The next method we looked at was an open source Stanford Policy Labs CCTV detector model. This model generates an object probability, so both detects and generates that object probability that that object is indeed a CCTV. This, on first pass, generated 32,000 potential CCTV objects. And again, we can click through and see just the general performance. The third model, we used another open source zero-shot method this time, Dino model with grounded pre-training, which also does not require any additional training and looks to identify and label the object. Also generating an object probability score, which you can see the distribution of here, and generates around the same amount, 29,000 objects. However, clicking around, you can see first off that there's no object probabilities above 85.5%. And clicking through these, there are a lot of air conditioning units that the model seems to classify as a CCTV. So potentially some problems right off the bat. And finally, we had a YOLO model that we used last year, and that one was trained to identify CCTV objects, but it was trained on entirely different video cohort and had a lot fewer image frames. So we were curious if it would perform well on a brand new video collection. Clicking through, it does not seem to catch many CCTVs, even though the object probability is very high. So the model is very confident that this is a CCTV, but in fact, it looks like a light pole. So again, some potential issues being seen with the YOLO model. So our next step was looking at potentially refining these models. Each of the models have a different distribution and different way of classifying the information. So I'll go over the refinement methods that we conducted for the segment anything with clip classifications. Segment anything with clip generated almost 1.2 million potential CCTV objects. That's too many to push to an analyst, so we were going to see if we can pare this down and refine this subset. Our first idea was to look at the clip score and generating maybe a cutoff threshold value. As you can see, that was the regularly distributed distribution before. So we can adjust the clip score and see how the method performs against previously labeled data. This is not our new cohort of video files. This is this is actually last year's video information that we can run the same model against and see how many times does clip think an object is a CCTV that was labeled also as a CCTV. And you can see our other common categories here as well. So the higher that we put this threshold, the more CCTV overlap, so the more clip agrees with our true labels, and also the less objects that we have. These are the suggested objects. So we are looking here to establish maybe a good cutoff to say that this is enough suggested CCTV objects to pass to an analyst without giving them too much or too little. So looking at that, 27 jumps up a little bit. There are still some light poles potentially within the data. But then we went to bring to 28. The number of CCTV object suggestions jumps down to 350. So I think we would like to err on the side of maybe including a little bit more data than a lot less. So we'll keep the 27 cutoff here. And now we've gone from 1 million CCTV suggestions to 1,063. But let's look if there's other methods that we can do to further refine. Looking through the images, we saw that a object on the car dashboard was frequently being identified as a CCTV, but we know that this is not an object that we care about, that we would like to push to our analyst to label. So what the team did is we just took a cropped image of this object and generated a clip embedding of the cropped image. From there, we ran similarity scores against all of the other masks that are available, this 1.1 thousand, and saw where the similarity score between the cropped embedding and the mask embedding were similar. And the ones where the similarity was very high, greater than 95%, we programmatically removed from our cohort. And here's a subset of 6 of the images that were removed. In total, removing those brought us down from 1,063 to 985 objects. And as a final pass, we looked at additional methods to potentially cluster and see just the distribution of the label suggestions themselves. So here is a clustering algorithm run within SAS Visual Analytics, where we generated the clip similarity score to CCTV, but as well as some other similar terminology. So light pole, street light, and window score. And then saw if the clusters maybe would fall and distribute in a way that can help us determine either known non-CCTV objects or true CCTV objects. As you can see clicking through here, some of them are widely distributed, but this cluster ID 1, does tend to capture all of these with the high CCTV camera score. And after some more analysis, we looked at just the distribution of clusters now across our almost 1,000 records. And you can see this is filtered down or sorted by the highest camera score. All the top ones are in cluster 1. The other thing is there's not actually that many that are listed in the remaining clusters that have not already been removed. So what we decided to do was just to keep cluster 1 within this subset. And this brings us down to a final object count after all of our refinement methods of 943. Again, that is a big decrease from our original 1.1 million. So after the refinement methods were conducted, we also looked at some accuracy metrics. First off, taking the top 100, we did not have labels right off the bat to assess these. So just to take a manual amount, took the top 100 and manually assessed, is this truly a CCTV or is it not? We saw the segment anything with clip really performing well. This was 68% actually before refinement, and then after refinement, the top 100 actually boosted up to 71%. And then the Stanford CCTV detector model also performed fairly well at 59%. Again, this is a brand new model with no pre-training on our data, still caught almost 6 out of 10. On the flip side, the grounding dyno and our previous year's YOLO model did not perform very well. We see 18% and 5% of accuracy. So we actually made the executive decision to just focus on segment anything with clip and the Stanford CCTV model and not even pass the results of grounding dyno or YOLO over to the analysts. So in the future, we could just start with these two methods and know that we would likely get some more accurate results. So the left-hand side looks at the increase of quality. And the right-hand side, we also wanted to reduce the quantity of labels that we pass to the analyst. We don't want them going through millions of records, potentially tagging the same object over and over again. So what we saw is the reduction that the refinement methods did on the volume of data. So the first pass for all the CCTVs, again, 1.2 million for everything. And then the refined total jumps all the way down just over 900 for segment anything, around 540 for the Stanford CCTV. And again, we chose to disregard the grounding dyno and the YOLO models. The total, that leaves us with 1,482 labels to pass to an analyst. Each of these have been deduplicated and deconflicted. When there was overlap, we chose the bounding box that was smaller or tighter around the object. So really, the aim is to make it as easy for the analyst to label and label the right information as quickly as they can. And finally, the deduplicated label suggestions are exported into JSON format, which can be seamlessly uploaded directly into Label Studio. After the CCTV suggested labels are reviewed by the analyst, the final labels will be fed right back to our team, and our goal is to tailor an object detection model, so fine-tune and train a YOLO model, and then run that model on the entire video cohort to detect additional CCTV cameras and assess the model performance. For results on those models, please visit us at the LAS Symposium or contact me directly at the below email address. Thank you.